Right now, trillions of dollars in capital rest on a single assumption that when an AI model hallucinates, the machine is defective. The tech industry treats these unpredictable outputs as a foundational flaw, something that can only be solved by building larger data centers and training models with billions of additional parameters. But compare a large language model to a standard programming compiler. When a traditional compiler hits an undefined behavior, it halts and returns an error. A language model operates differently. When it hits a gap in its instructions, it uses statistical probability to generate a plausible assumption. It fills the silence with a guess. We are misdiagnosing this failure. What we call hallucination is actually specification-induced speculation. It is a mechanical reaction to underspecified human input. This animation shows the contrast. A standard, open-ended prompt allows the model to produce a chaotic web of diverging outputs. However, constraining that input within a strict geometric corridor collapses that probability. The branching web becomes a single deterministic line. The industry is treating the machine for a disease that actually resides in the human input. This creates an architectural paradox. We are demanding mathematically reliable logic from an engine built entirely on statistical probabilities. Resolving this contradiction requires a principle called bounded stochasticity. Instead of dictating the internal choices of the AI, we restrict the output space using structural invariance. We eliminate the model's capacity for guesswork. The mechanism designed to enforce these invariants is the Software Development Prompting Framework, or SDPF. It is a formal language that removes the ambiguity between human intent and AI execution. Applying the framework binds the AI model to a mechanical role. The system executes the specific parameters of the contract, operating as a compiler that ignores probabilistic improvisation. Predictable code generation requires a shift in focus. We must stop demanding deterministic behavior from the model and start mandating a deterministic specification. Consider a developer using AI to build a private peer-to-peer messaging application. A project requires 4 distinct layers: user interface pages, database schemas, business logic services, and unit tests. This architecture map shows empty gaps separating the layers. Without enforced contracts, these unverified boundaries create structural gaps where the AI must improvise. The red dashed lines show the result. The model generates a UI hook that doesn't match the service layer, breaking the system. The consequences are measurable in time and budget. Reaching a working application under these conditions typically requires 12 to 24 manual correction cycles just to resolve the integration failures between these layers. This proves why optimizing a prompt with tone or few shy examples is ineffective. A wrapper cannot enforce the missing mathematical contracts at these unverified boundaries. The SDPF lifecycle uses a rigid barrier to prevent these gaps. As seen in this timeline, the framework separates problem identification from code delivery with a mechanical gate lock. Phase 0 must be completed before any implementation begins. This rigid gating is a mathematical necessity. Large language models possess no capacity to validate human intent. They only blindly execute the parameters they receive. Once the problem is formally observed and defined, the gate unlocks. We move into Phase 1, where the problem is translated into the technical specification prompt. The TSP avoids conversational English. It uses dense, code-like formatting, governed by priority tags: critical, required, and optional. These tags dictate exactly which logic wins if the AI encounters competing parameters during generation. Every requirement within this document is assigned a unique REQ ID. This establishes an absolute line of traceability from the initial prompt through to the final codebase. Enforcing this Phase 0 barrier prevents the most expensive error in AI-assisted engineering, perfectly generating code that solves the entirely wrong problem. Even a structured specification will fail if it relies on imagined facts. AI models frequently assert stale historical data, like deprecated API endpoints or dead command line flags found in their training sets. To neutralize this, SDPF mandates Core Principle 2, facts before execution. The framework relies on a technical verification gate, acting as a mandatory filter that blocks code generation until the specification matches the live system. Every TVG entry requires 4 components: target asset, verification command, pass condition, and halt rule. The framework fires this command against the live environment to verify endpoints. If the system returns a mismatch, the gate physically halts the process. The pipeline is severed. This eliminates the habit of using silent version shims to turn a build green. It forces a resolution between the specification and operational reality. Building a microservice requires different structural invariants than generating a mobile user interface. This matrix shows how the framework manages this variety. It uses 17 distinct SDPF styles. These are specialized dialects optimized for specific architectures, such as Style 1 for APIs or Style 12 for sovereign ledgers. Utilizing a specific dialect maps the exact physical and logical laws of the target environment onto the prompt. These styles ensure the model remains firmly constrained by the reality of its assigned task. The final stage of the lifecycle is governed by Principle 3, verification always. No release is permitted without a complete closure record. The final output is an SDPF evidence package. It contains the locked specification, the base test suites, and an implementation hash, all sealed with a cryptographic provenance signature. For highly regulated sectors like medicine or aviation, this tamper-evident artifact provides the empirical proof required for external audits. It links every code function directly to a business requirement. This creates a chain of accountability. Total liability rests on the human architect who authored the specification, removing the ability to attribute systemic failures to the AI model. Current industry benchmarks primarily measure an AI's ability to guess under uncertainty. By testing for gap filling, these metrics favor massive models with high parameter counts. However, testing for execution fidelity, the ability to precisely follow a mathematically complete specification, shows a significant shift in model rankings. This chart plots that fidelity. When provided with a complete specification, a 7 billion parameter model matches the precision of models 100 times its size. The smaller model achieves total execution fidelity because the input has removed all room for improvisation. This suggests that massive infrastructure scaling may be providing diminishing returns for reliability. Trillion-dollar investments in parameter counts are often used to mask underspecified inputs, providing a plausible guess where a precise instruction was actually required. The technology for reliable AI is already present. Success in this era depends on the engineer's capacity for specification discipline. In this environment, the specification is the program, and the AI is the compiler.